So, not here. I'll just quickly answer one exam. Can you go to the Oceani for midterm? So think about it, guys. Read instructions. The instructions for that exam will tell you how do you submit the exam, how do you provide answers, and most importantly, whom can you consult? And it says this: if I find out that any question, even one question, was on the internet or shared and it was without me present, I will fail you for that exam. Good. So the answer is it's an exam. You have a lot of time to do it and you're supposed to know the material. If you have questions, I will definitely help you guys. I'll do my best to help you. As you notice, I try. But if you post it online on some websites, and if I end up finding it out, or if I suspect that you posted, I might ask you personal questions, right? Interrogate you. So none of it is pleasant, not to me for sure. So let's not have it the situation. Last semester, I told you by the time I graded the final, I caught about half the students in my small probability class. You know, I do it by many ways: psychological pressure, and of course forensics. You understand? So make sure that we don't get to the situation. Yes, I do give partial credit, of course, right? But try to get it all right. So here is the first question, just quickly. Guys, one of my cats, Spuntik, is a fussy eater. Give him the same dish more than once in an interval of 3 days and he will not eat it. If I have an assortment of 5 dish types, in other words, each dish type is 10 copies. You see, I mean, I could have given each dish again and again and again each day. That's the point here. Right? It's not important that it's 10 here. How many menus can I make for the next 10 days? And I have to make menus where the cat is eating the food. So what's the situation? So it's very simply, you have first day, second day, third day, fourth day, fifth day, and onwards, right? Make sure, guys, especially for harder questions, to indicate how you solve it. Good. So notice what's the situation. So I have 5 types. So here I can select any of 5 types. This same type is not available, so I have 4 types. This is not available. I have 3 types. You see, because I cannot access first or second. So 3 types. Now, fourth day, what has happened? One of the days, now one of the dishes has renewed and one dish is lost. So the rest are just 3. So this is 3, 3, 3, and onward. So basically we have from 3 all the way to 10, we have how many numbers? We have 10 minus 3 plus 1, which is 8. So the answer is 5 times 4 times 3 to the power of 8. Clear? Whoever asked that question, guys, I hope it's clear. Now let's move to the to the current material. The exam will be during spring break, right? So guys, one thing I want to make sure is all of you are on my mailing list, correct? So if you are not, guys, make sure to send me a message to my email at Yahoo that I mentioned. And yes, you will be notified. Okay, relax. I will do my best to accommodate you. But of course, guys, PDF format, try to keep it uniform, try to make it easy for me to grade. We'll speak about it later. Conditional probability should not be on the exam. Well, of course, we know a little bit of it, but that's second exam. The syllabus mentions chapter 1 and chapter 2, which do not involve conditional probability. You see, I grouped it by chapters. Chapter 1, 2, right? I mean, sorry, this is, it's grouped here. You see 1, 2, 3, 4, 5, 6. Understood? Chapter 1 and 2, 3 and 4 are second exam, and the final is cumulative. So did we finish multiplication? Or I don't remember. Let me see. No, we have not, right? No, that's right, we haven't. So I believe, if I'm not wrong, guys, correct me if I'm not wrong, we were speaking about multiple choice questions. And I think I left it as a cliffhanger, right? Will you get the right answer or not? So a multiple choice question with m possible answers appears on an exam. The probability that student knows the right answer to this question is some probability p, which was obtained by statistics, by giving this question open-ended to a lot of people. Good. So we have an estimate of the probability p. The probability that the student answers correctly by guessing is that he selects or she selects 1 out of m possibilities. What is the probability that student knew the answer, even given that the answer was correctly given? Clear? So just because somebody answered something correctly does not mean the person knew it. The question is, what's the probability that it was not just a guess? Thank you, Erin. Well, let's do the answer together, guys. So here is how I set it up. In this section, we learn to use symbols, like letters and whatnot, right? So K be the event that student knows the answer, and C be the event that student answered correctly. Then we're interested in the probability of K given C. Very difficult to calculate this way, but according to conditional probability, this is the probability of knowing answer and answering it correctly divided by probability of answering correctly. All good? And so what's the probability? What is the numerator? No, numerator is simply, I can condition it. It's the probability of knowing the answer multiplied by the probability of giving the correct answer given knowing. Do you understand this? We're using the multiplication rule, which I hope you understand. So And the denominator can be also broken into two disjoint events: probability correct answer and the person knows, and probability correct answer and person doesn't know, which can be also conditioned. Right? I can basically it's CK union C not K, which gives me this denominator. So what we have here, so we are assuming that the probability of correct, given that the answer is known, it's not fully true, but let's suppose that the person will not make a mistake. So that would be 1. Probability of correct answer giving knowledge is 1. Probability of knowledge is P, divided by 1 times P plus 1 over M. That's probability of correct by just guessing, times 1 minus P. So, I mean, in SATs, I presume they use such idea to know how much to deduct, to decide how many points you want to deduct when you give incorrect answer, to prevent guessing, to discourage guessing. So, for instance, suppose only 10% of the student population know the answer to a given multiple choice question. Suppose 5 possible answers are offered. Then the probability that knowing knowledge is there, giving correct answer, is about 0.36 or 36%. Isn't it interesting, right? So knowledge given correct answer is actually not very high. You see, it's more likely that it's not 10%, but it's not very high. You would think if somebody gave the correct answer that they know the answer. That's not true. But because I suppose 10% is not so small. I mean, enough people know it, and it's possible enough to guess. Well, yes, I didn't prepare. I forgot. I should have prepared you a video. Have you ever wanted to pet a lion? No? I mean, there is a pretty nice zoo. I can show you what it is if I can find it. Taigan. You want me to show you that zoo? Let me see if I can quickly find it. I should have prepared, but let's see. And give me one moment, guys. One small moment. So, I mean, I just opened one of them. There is one in English for English-speaking tourists. But here is the thing.
Да.
Here it is. So
Удержите.
you go.
Держите меня, 7, а 8 не удержите.
You go onto the bus, and the lion comes in.
Это
And you
да.
pet the lion.
Повезло так повезло.
Yeah, so you understand the idea, right? So there is this reserve. I can, if I find it, they have a commercial in English if you ever want to travel and get to pet a lion, right? It's pretty fashionable. Good. So that, of course, requires us to know conditional probability. An autistic savant wishes to pet a lion in a Russian zoo. He cannot tell a bad lion from a good lion, but knows that the bad lion bites with probability 0.9 and the good lion bites with probability 0.4. If the savant gets mauled by a lion, what is the probability that he went to pet the bad lion? Here is the choices. Go ahead, calculate. Oh yeah, I found the English version, sure. So if you want English tours, you can have them as well. Thank you, Fiona. Tiger King? So, no, I haven't seen it. Thank you, Andre. In the photograph, Abhishek. All right, 9/13, it seems. Good. Where did you all go, guys? I had more of you. You disappear. All right. I think you get it. Yes, guys? So here is the layout. So let B be the event that byline gets to be pet, and M be the event that the savant gets mauled by the lion. So we are interested in the probability of bad line given that there was a line that mauled. And so what's that probability? That simply is probability of M and B divided by probability M, which is probability M given B times probability B. Well, you know, I think you understand it, right? I don't even want to mention it, correct? Just condition it, and then assuming that probability of petting B is the same as probability of petting B complement, the good line, are the same. That means that we have 1/2 here. So the probability is simply 0.9 divided by 0.9 plus 0.4, or 9/16, which is only 69%. All right. Here is another example, right, of conditional probability that may surprise you. Vasya is tested for a disease that affects 1% of the population. The test result is positive. Assuming this test is 95% reliable, what is the probability that Vasya is afflicted with the illness, guys? So first of all, you have this test. It's 95% reliable, and it afflicts 1% of the population. So if the test came positive, should this person be very worried? So do you understand, guys, what is 95% reliable supposed to mean? It means that if you have the disease, it will identify that you have the disease with 95% likelihood. And if you don't have the disease, it will also indicate that with 95% likelihood the disease is not present. All right, thank you, Andre. So in other words, Jennifer and Andre, you're saying it's only 16% likely that the person is ill. Seems low, so you think it's much higher, yes, Roadra, I'm sorry. Yes. Ben Hatch. Okay. Okay, Andre, yes, okay. Let's now see the situation. So here is the way I set it up, guys. You just come up with good symbols or with some symbols. So I say D is the event that Vasya has the disease. T is the event that the result is positive. 95% reliability means that test is positive when the disease is present with probability 0.95, and the test is negative when the disease is absent is 0.95. Makes sense, yes? So in the particular pool of people that have the disease or don't have the disease, that's the 95% reliability. We know that the population is maybe by some more reliable tests or by some sort of other measures, we estimate that in the population, the prevalence is 1%. So what do we get? We get that the probability of disease given test is positive is the same as probability of test positive given disease, probability of disease, divided by test positive given disease, probability of disease, plus test positive given no disease, probability of no disease. Everybody understands how I get to that formula, correct, guys? I am rather fast at moving through it, but you all understand how that formula appears, correct? All I do is I use the multiplication rule, just to be sure. What do I use here, guys? So probability of disease given T, I simply just say, okay, what is that? That's probability of disease and T, and test positive, probability test positive. That's the conditional probability, definition of conditional probability, which I tried to justify earlier, maybe last lecture, or the lecture before we justified it. Good. And then from there, you can simply rearrange the numerator. The numerator simply, instead of, we can expand it first D and then T, instead of first expanding T and then D. Right. So we can say that this intersection is the same as probability of disease being present times the probability of test given disease. That's the multiplication rule. And the denominator, we simply say that T is T intersect D union T intersect D complement. Very simple. Yes, guys, it's just we're using we just, if we have the symbols, it should be fairly fast. So having calculated, we get 16%. And of course, some people think that this is very low. They imagine test seems very good, 95% reliable. And they think that if the test is positive, then that means that it's very likely you have the disease. They think maybe, I presume, I'm not sure what you think, but I presume maybe close to 90% or 95%, right? That's what you imagine the probability to be. How is, FNU is asking, how is probability of test positive given no disease is 1 minus 0.95. Let's see. So this part, right? So look at it. If there is no disease, the test is either positive or negative, right? So how should I say that? So there is no disease. We have this situation. No. let's look at, well, let's look only here, right? So what do we have here? We have that we either have test is positive or test is negative given D. Now there are disjoint events. I mean, again, we're within D complement. I'm sorry, within D complement. That's our new sample space. In other words, we know we have no disease, and among the people that have no disease, all of them, we have those that we test with this test, and they have a positive. And we have those we test, and they have a negative. That's called, in this case, a false positive. And I want to know what's the likelihood of a false positive. So I know that 1 is going to be the sum right? Because I'm just restricting to a different sample space. I have a list of the healthy people, and I am applying the test to healthy people. Does it make sense? So if all the healthy people receive the test, exactly how many of them will be identified as negative? How many of them will have T complement? Exactly 95% of them, and therefore exactly 5% of them will be identified as T plus, T positive. Good. Okay, so the answer is by this calculation is 16%. Let me show you with a picture, with a diagram, why that's not so surprising, why it should not be actually close to 90%. Or I'm not sure what other number you imagine, if you're surprised by it. Right, so here is, let's suppose we have 10,000 people. Good. Thereby, by the way, make sure that maybe I made some mistake here. I think I might have when I was writing it. I don't remember, right? Somebody, I think, mentioned something I faintly recall. So let's see. So if we have 10,000 people, how many of them are diseased? 100. So I removed 2 zeros, and I have 100 people actually have the disease. So I have a list of 100 people with the disease, and how many healthy? 9,900. Good. Now, of the people that are diseased, how many of them the test will identify correctly as having it? 95%, which means 95 of them, correct? So 95% of them will be true positives. And how many of them will be negatives? 5 people, 5%. On the other hand, on this side, yeah, how many of them will be identified? Of the healthy, how many of them will be identified as not having the disease? They are healthy people. 95% of them will be identified as not having the disease. Calculate 95% of them. This is the number, I presume, right? Hopefully, I'm not making some algebraic, some arithmetic error. That's 95% of them, and only 5% of them will be identified as having as tested positive. But because this is a large number, basically 5% identified with false positive gives us quite a lot of people compared to the true positive. So what is the probability given that test is positive? If test is positive, I'm either in this branch or in this branch. Those are the only ones where test is positive. And if I select randomly a person in here, guys, are you seeing? Then the denominator has 95 plus 495. So how many true sick people are here? 95 over this number. Understand? That's going to be that probability done in a diagram. Do you see that? The fact that the test is, it seems fairly reliable, there are just a lot of people, a lot of opportunities to still make a mistake. You understand? So there are, yes, so there are many opportunities to make a mistake. And so the mistakes, they will gather enough until you have this fraction. Good? Now we can continue this problem. Now suppose so Vasya should not be, I presume, as worried as Vasya initially was worried, right? And should not, by the way, rush to test centers, as people sometimes do that, right? Because they're hypochondriacs.
Professor.
Yes.
So in exam, can we answer like just the way you solved the last program using diagram? Can we answer like that? I mean, like before using any formula.
If there is a problem that can be answered by a diagram, yes. But I mean, if the answer is correct, it's fine with me. Just I think symbolically, it's up to you again. If it's a correct answer and it's the logic is there, I'll give you the credit. You can answer it any which way you like.
Thank you, Professor.
I don't see. I see. Maybe that gives you a better sense. I'm not sure. It gives you an intuition, perhaps, but symbolically you get the same answer. Right? Drawing those lines can be a bit annoying. So suppose that Vasya wants to test again, right? To be sure, maybe one more test will be more convincing, right? Maybe if it comes up again positive, then a person has the disease. So he tests again, and suppose that again the result is positive. What's the likelihood of Vasya being ill with the disease? So he tested one more time, and again the test comes positive. What's the likelihood of? And let's say the test is independent. In other words, we don't, the independent administrators give that test. What's the probability of being ill this time? All right, guys, so let's do it together. Again, right, so if he tested positive again, first of all, he could have belonged to the original population of people that tested positive previously, right? And those involved the 95 that are truly sick and 495 that are not. So how many of them, of the 95, will test positive? If my arithmetic is, and again, check my arithmetic, guys. The idea is you take 5% here. Sorry, you take 95% here. That's this thing. And over here, you test positive, you take 5% here. I'm not sure if that's the number, but yes, I think if I calculate correctly, 78%. Good. Simply, there might have been an error. I don't remember. I don't want to check the arithmetic, guys. You see what I'm saying is that you take along this branch, you take 95%. Along this branch, you tested positive twice. So it's either this branch or this branch where he's located. So in this branch, he is among about 90.25. And over here, he is among, just take 5% of this number. So 2 test positive, if I calculate it correctly, means 78% likelihood of this disease being in this person. Here is another question. In an ongoing criminal investigation, the inspector is 60% certain that the suspect is guilty. New evidence shows that the perpetrator of the crime is left-handed. The suspect is left-handed. If 20% of the population are left-handed, how certain should the inspector be of the guilt of his suspect? You understand? So initially, based on every evidence we gathered so far, the probability of guilt of the suspect is 0.6. Now, new evidence comes in. Here is that new evidence. Left-handedness, 20% of the population are left-handed. The suspect is also left-handed. What's the, it's certain that the perpetrator is left-handed. It's certain that there was one perpetrator, let's say, whatever, right? So what's the probability now that he is guilty? Okay, thank you. Nora, thanks. Okay, we have 288. All right, so a few people answered. I hope the rest of you guys, you understand how to do this problem, right? So it's straightforward how to set it up at least. So this is the situation. So I say G is guilt and L is left-handedness. Event suspect is left-handed. So you understand, guys, a matter here is you want to make sure that you can come up with symbols. If you can come up with symbols, it's fairly simple to solve it. So we want to know probability of guilt given left-handedness, given that suspect is left-handed. So that means probability of left-handedness given the person is guilty. The guilty person has to be left-handed, so that's 1 times probability of guilt. This is the same thing. Now the second part is probability of left-handedness given that probability the suspect will be left-handed given that this person is not guilty. Now that means he's just an innocent member of the population, and that's 20% of the population, so it's 0.2. Understand? So this would be 0.2 and this would be 0.4, and the answer is approximately 88%, as those that replied, most of you said. Now, there is an obvious generalization of Bayes' formula. We don't have to have two categories by which we condition. There could be arbitrary. So for instance, suppose we have finitely many. They, by the way, don't have to be finitely many. They just have to be disjoint. So here is one, here is another. There are n categories, and they are mutually exclusive events, with the assumption that S is equal to the union of all those events. Then if E then will be equal to the union of E intersect each event separately, and because they are disjoint events, probability of E is probability of EF1 plus probability EF2 plus probability EFN. And I can condition each of them, and I create this type of sum, right? This is just E given F1 happening, and E given F2 happening, and so on and so forth. Clear? It's just follows symbolically. Agreed, guys? You just add out, so everybody understands this formula, or do I need to explain a little more? Make sure that before I skip over that we are all together. Do I need to explain, guys, more, or do you understand it? Please say yes if I need to explain more. Otherwise, I'm moving on.
Can you explain it again?
Well, okay, so this is the situation. So we have the set S. And imagine that the set S is divided into several segments. So this is F1. This is, decided like this. This is F1, F2, F3, F4. Now the event E can intersect all of them, right? So what is E? So what is this region here? This region here is E intersect F1. And this region here is E intersect F2, and so on, right? So what's the probability of E? The probability of E can be the sum of the this probability, this probability, this probability, and this probability. So what I'm saying is that the probability of E is simply the probability of E and F1 plus probability of E and F2, E and F3, E, F4. Yes? Do you hear
Yes.
the noise, or the noise do not come through?
Yeah, we can
You do,
hear.
right? Okay.
But it's okay, Arkady. It's all right.
It's fine.
All
I'll
right.
let him go. Let's give me a second. Go. He doesn't like my class. Yes. So, but that's because he doesn't understand how brilliant I am, right? How interesting this what I'm describing. So here we have this all those intersections, right? This is F4. So I can condition each of them. So for example, what is this? This is probability of E given F1, probability of F1. You agree? That's just a multiplication rule applied to two events where I begin with F1 and condition based on F1. And when it's useful, it's when it's easy to calculate, let's say, the proportion of this red region to the white region, but not the red region to the whole. Good? So I just partitioned it like this. You will see in a moment how that's done with particular examples. So here it is. So a plane is missing, and it's presumed that it was equally likely to have gone down in any of three possible regions. You understand? So there are three regions, and let's suppose that 1 minus bk is the probability that the plane will be found upon a search of the kf region. So b sub k is the overlook probability. In other words, imagine that we know something about those regions, and maybe statistically we figured out how likely it is for the plane to be found if it's searched in that region. Okay, if the plane is in a particular region, how likely would the searchers find it? And we have those estimates. They are B1, B2, B3 based on the properties of the region that probably it's obtained statistically. Right? You just kind of hide an item and then search for it. Right? Like kind of you take an item and put it in my brother's room and try to find this item. Then of course the probability, the overlook probability is very high because you cannot find anything there. So the question is, what's the probability that the plane is in region K if a search of region 1 was unsuccessful? Do you understand my question? It's symbolic here because I haven't given particular numbers. The bigger is BK, the less likely the plane to be found in that region, even if it's there. Good, so region 1 was searched. The plane is in either region 1 or region 2 or region 3. Region 1 was searched, plane was not found. Either it was not found because the plane is not there, or it was not found because the search was not thorough enough. What's the probability the plane is in any region, region 1, region 2, region 3, given that search of region 1 is unsuccessful? That's the question. So guys, just one small interruption. Oh, it's a very big cat I see, Sarah. Nice. There was apparently an announcement on Blackboard that there is some exam on April 12th. I don't know, guys. Who knows? Maybe I played with Blackboard and and something popped out. Ignore until you're told by my email, by me personally. Okay, very simple. Don't worry. The exam is when I say the exam is. Victoria, good. I answered your question, I hope. What is her name, Sarah?
Juno.
Juno? Yunona, okay. There is a nice Russian opera called Yunona и Avось. It's a rock opera, whatever they call it. I can play afterwards.
She loves Russian opera, so.
Good. This one is very good. It means I will never forget you and I will never see you. Maybe I'll play it after if anybody is interested. It's about America, actually. Anyhow, sorry, let me not distract you. We'll talk about it later. Maybe. All right. I guess let's do it together. It's hopefully, guys, it's just it's not difficult for you. So here is the situation. So first of all, I need to figure out some notation for the event that the plane is in region 1, 2, 3. And so I label by RK the event that plane is in region K. And F1 is the event that plane was not found in region 1, not found, F1, okay? Clear? F1 means not found. So I'm interested in the probability, for instance, of a plane being in region 1, given that it was not found in region 1. Now the plane is, so I just condition this. Upon conditioning, look what I do. I just need to reverse. I know what is F1 given R1. You agree? So in the numerator, it's F1 given R1 times probability of R1 divided by F1. Now, F1 can be conditioned on R1, R2, and R3, and that's how I get the denominator. Everybody is clear? Good. So then, of course, probability of R1, R2, and R3 are the same. They are 1/3 initially. That's the initial probability the plane is in that region. I can cross them out, and I see that probability is F1 given R1, meaning that the plane is not found given it's in R1. That's the overlook probability. Divided by what? So probability F1 given R1, that's B1. The probability that the plane is not found in region 1 given that the plane is in R2 is 1. And the probability plane is not found in region 1 given that the plane is actually in R3 is also 1. So I have B1 over B1 plus 2, where B1 is how hard it is to search, how hard it is to search in that area. If K is not equal to 1, I get a very similar result. I just get F1 given RK, where K is either 1 or 2, and the numerator is 1, and the denominator is the same. So notice 1 is always bigger than or equal to B1. So, so basically, clearly the probability that it is in another region is bigger than the probability it is in region 1. And that probability, and the probabilities, they converge to the same value as before, if of course it's very hard to find the plane. Are you clear, guys? You understand how this calculation was carried out? Yes? No? Okay, where have I lost you guys? It's this thing, look at it. Let me just, it's just this part, okay? From this part, can you set it like this? So probability of R1 and F1, it's not convenient. So you just write it as probability of F1 R1 divided by probability of F1, right? So I want to know the probability the plane will be found in region 1. But so how do I do the denominator? The denominator, I can write F1 R1 union F1 R2 union F1 R3, because the plane is necessarily either in 1 or 2 or 3 by the assumptions of this problem. Do you agree? So so I can write what's the probability not found in 1, given that the plane actually is in 1 or 2 or 3 regions. Those are disjoint events, so I can break them apart and I write summation, and then I can condition. Right? How do I condition the numerator? That's simply probability that the plane is in R1 times the probability that the plane is not found in 1, given that it is in R1. Good? Guys, I hope I'm not moving way too fast and you understand me, correct? You are understanding me? If not, let me know. I will repeat whatever is necessary to repeat. Just ask me questions.
Can you just clarify what or how you knocked out the probability of R1, R2?
Yes, because initially I was told that the plane is equally likely to be in which one of them. So,
Okay.
so the relative area, if I represent it by area, the area of the strip R1 is 1/3 of that full space. Each of them is just basically I divide the rectangle that's my full sample space into 3 regions. There maybe the areas are equal, or just somehow the plane is equally likely to be in all of them. So they are equal areas in the probability representation.
Okay, thank you.
Good. I understand the top part, but I'm confused where we get B1. I don't think there is a B1. Is there a B1? There is, you mean this thing, okay. That's the overlook probability. So, I mean, it's something that you cannot, without me giving you a lot of extra information, and most likely without you conducting experiments. For example, imagine that I want to estimate how hard it is to find this pen in this particular room. How do I do that, right? How do I figure out the overlook probability, right? So in other words, suppose that I place this pen somewhere in this room and I make somebody search for it, right? And I do it again and again and again, and I just calculate the ratio, how many times the pen was found over how many times the pen was searched. And that will give me the probability of an item being found. Or if I prefer the item not being found, that would be the B, right? How many times the item was not found divided by the number of times the room was searched. That would be the way I can empirically, experimentally estimate the overlook probability. Is that clear? Right? Which I need to know is because some searches will not yield a find. Even if the item is there, you will not find the item just because you were not able to search well enough. Good? So that's the overlook probability, which we are not concerned with. It's given to us. There are some statistic tables, or somebody else did this experiment. Good. That's how this B1 is obtained. B1, B2, B3 are typical to the particular places. This is room 1, room 2, room 3. B1 is the overlook probability. In other words, if the item is there, what's the likelihood that it will not be found if you search for it? Good. So that's written theoretically, but you understand statistically how you might estimate it, perhaps. Great. Then here is another simple question, hopefully. So there are 3 types of flashlights in a bin. There is type 1 flashlight, and it works for more than 100 hours, and the probability it works more than 100 hours is 0.7. And it constitutes 20% of all items in the bin. flashlight of type 2 will work with probability 0.4 longer than 100 hours. And of type 3, 0.3. It's the worst flashlight here. Good. So this is the proportion of the flashlights in the bin. So if you randomly select a flashlight, what is the probability that it will work more than 100 hours? Are you clear the question? Just randomly you pick whatever flashlight, maybe select a number and the flashlight is given to you. What's the probability it will work longer than 100 hours? Kunyuan, thank you. And thank you, Ben. You're all correct so far. Okay, Alan, thank you. And Fnu and Roadra, thank you. Okay, great. All right, ready? So how do we do that? So we have flashlight A, B, and C. Good. Those are the events. So I want to know the probability, and H will mean working longer than 100 hours. Okay. So if I have H, it's either H and A. In other words, working longer than 100 hours in its flashlight A, or flashlight B, or flashlight C. Good. Which are disjoint. And then I can condition each of them. All right. So probability working longer than 100 given its flashlight A times probability of A, then the same for B and C. So what do we get? We get 0.41 or 14 over, sorry, so we get 0.41 pretty much, that's good. 0.41. Now, I want to know, given that the flashlight lasted over 100 hours, what's the conditional probability it was of type J, where J is either 1, 2, or 3. So you have to calculate for each 1, 2, and 3. If you already know it lasted more than 100 hours, what's the probability it's type 1? What's the probability it's type 2 or 3? All right, Fnu, that's good. You're fast. Okay, great. Erin, wonderful. Okay, great. Ruadra, wonderful. So guys, it's not too hard, yes? I mean, do I need to wait longer or you understand it? Okay, Alan. Good. Here is the situation. So we know that probability of H is 0.41. So probability of A given H is the probability of H given A times probability A divided by probability H, which is 14 over 41. Then we have 12 over 41 and 15 over 41, same calculations. Now we are up to this point, guys. We can say a little bit about how we calculate probability. This is a somewhat strange example, but maybe it will explain to you how you may assume more information than you actually have in solving probability questions. So 1 of 4 fair dice will be chosen and tossed twice. For example, that might be the blue or the red or the yellow or the white. They are each fair. Given that the sum of the dice is 7, what is the probability that the numbers 1 and 6 came up? Can you calculate it? Is before I say anything? So you understand, a die will be randomly chosen and then it will be tossed twice. And I want to know that if the summation came to be 7, what's the probability that 1 and 6 were the numbers on the first and second toss? Maybe not in that order. So Fnus, you're saying 1 out of 3. Are those the only outcomes? The thing is, we are saying that we know that the sum is 7, and the question is, what's the probability that the numbers 1 and 6 came out? So yes, right. So we have 2 possibilities, 1 and 6 and 1 out of 6 possibilities, right? So it's 1/3. Good. But my point is, guys, do you understand when you said it's 1/3, you completely ignored the selection of the die, which means you assume that the die that was tossed is either yellow. Maybe you just not either. You assume that the die that you were tossing is yellow. You understand? Or maybe you assumed it's red. It doesn't matter. In each, basically, you can imagine that in each universe where you jump in, where the selection was maybe the red die or the yellow die or whatever it is, the result is the same. So it doesn't matter whether you are in the red die universe or yellow die universe or something else. And now let me show you formally that you assume more information. You understand? So many of you, when you do probability or when you did probability before, you said that you discard away the color of the die, but that's not what I do. I don't discard, I assume that I know the color of the die. So the die was selected somehow, maybe randomly, maybe not. I assume that I know which die was selected. Many of you will assume that it doesn't matter and you don't have it. You just throw this information out. I just assume I know this information. It's in my protocol. That's what I'm trying to say. So here is how I solve it, guys. So first, the sample space for the problem as stated it's a bit bigger, right? It's the type of die. So I can imagine the die is 1, 2, 3, or 4. It's the type of die, then the result of first roll, then the result of second roll. Do you agree? What I'm saying is that this entry I can imagine filled in. This is filled in, what I'm trying to justify. So suppose that the probability of picking up die number k is p sub k, which doesn't matter how it is. You see, it's just some probability, or maybe it's equal to 1 and the others are 0. You see, it's some probability with which I will pick die number k. So I can say that the probability that 6 and 1 came, given that sum is 7, is simply this probability. It's the probability 6 and 1 and sum is 7 divided by probability of sum equal to 7. Now sum is equal to 7 either given die 1 or die 2 or die 3 or die 4, or right, it's just any particular particular die. So here I add that information. That's why the summation comes about, right? Is that I either got a 7 with die number 1, or a 7 with die number 2, or a 7 with die number 3, and onwards, right? Say similarly the summation with those dice. And then I can condition it. I can say I condition it, and then I realize that the result is just this summation, right? It's just the summation, which is really, I can assume, because now the result, if it's die 1, this condition is not affected, right? Given that it's die 1, summation, this probability is the same as if it's die 2, die 3. So I change the index. Do you see it? I change the index from an arbitrary k to the index 1. And that allows me to factor out this part out of the summation. And in the denominator, I can factor out that part given summation. And this cancels out, and I get 1/3. I hope you understood what I just did, guys. I did something. If you haven't, I'm just trying to show you that you assume that there is no box here. Whereas I assume that there is this box, but I filled it in. Just like when I mentioned that I assume the universe is just very more definite than in fact the problem tells me it is. Are you following me? That was the reason that that in the previous examples, the probability of the favorite food affected whether we have 2 brown dogs or not. Right? Because it has nothing to do with affecting the dog's brown fur. It has everything to do with the universes in which you're located. Good. So that just you have to be careful not to discard information, but to use it correctly, because each information gives some information. There's no information that will not tell you more about this universe, that will not make this universe more definite. But sometimes that information will not influence the probability. Make sense? Wonderful, guys. So our time is up. Do you want to see a what when where question? I have a few of them that are a bit interesting. Do you want to listen to 4 minutes, in a voice? Maybe you don't, right? I don't want to torture you with that, right? So Jack is honest. I like that. Jack doesn't want because he already has forgotten, right? It's a very, very good song, but I don't know, maybe it will not pierce your stone heart. As I heard in one ceremony, apparently the only thing you have in your soul is a place for stones.